Okay, Le Chatelier's principle and the video that comes after equilibrium here, more about equilibrium. I'm going to talk about Le Chatelier just real quick because sometimes I think it's important you know the scientist and where this information comes from. Le Chatelier, he was French, his first name was Henry Louise, or that's because I'm country. I say Henry Louise, but it's French, so it's probably like Henry Louis Le Chatelier. He was a French scientist, and he was around 1920s, 1930s is when he lived and developed all of these principles in France. He came from a really smart family. I know that they were engineers and they had like a metal working factory. So the fact that he ended up coming up with chemistry principles that are in a aqueous solution is still kind of fascinating to me. But anywho, he came from a family of a bunch of really smart people. And as it turns out, even though he was an engineer and real smart and chemical engineer and all that, he lived in a time where if you were a scientist, you were a rock star, much like the atomic theory presentation where all those guys were like rock stars. But Le Chatelier was a little bit more down to earth, and he was a teacher. He was part of a educational reform process that took off in those early 1900s and has much led to how we develop like collegiate organizations today. And he was also a father. He had lots of children. I want to say like 7 comes to mind. The majority of them were girls. So, he was a great thinker and thought about things and came up with a lot of these principles where he wrote them down and was able to explain them and became, a very good teacher, well respected, which led to reform. Although I find it fascinating how anybody can sit around their house and think about anything deep and meaningful with a bunch of children running around in the background. So he must have had a wife that was amazing and took care of them while he went into his own little study and had quiet time. Just saying. So what is Le Chatelier's principle? Le Chatelier said that any changes or stress, if you put it on a reaction, it will affect the position of equilibrium and that direction and the direction that it's going. And by direction, I mean, is it going to the left or is it going to the right? Wherever you put the stress and you put the change will affect, where the reaction is hanging out. And it also states that it will shift away from the added component and shift toward the component that's been removed. Like if I'm adding something to the system, then it's going to shift away from that to make more of the other thing. And if I'm shifting toward, if I remove something from the system, then it's going to shift toward that component to like fill in the space of what should be there. And so how does the system at equilibrium respond to change? Change affects the equilibrium position. So when you stress the reaction in some manner, you change its direction. You change the direction away from stuff that's added and toward the area where you've removed something. So for example, here I have a reaction. Nitrogen gas plus hydrogen gas makes ammonia. And vice versa. If I have ammonia in a container, it will make hydrogen and nitrogen gas. And so we're talking about gases, right? And we're talking about these gases kind of like sitting in a container, like hanging out. And oftentimes you see this double arrow. It's like a little half arrow. And that demonstrates that the container, the reaction is in equilibrium. Okay, so let's just say I continue to add and add and add and add and add H2 to my container here. What do you think will happen? Well, the reaction's going to move to the right. Because I'm adding all of this hydrogen here, it wants to maintain an equal balance. So it's going to start to make more product so that the product side starts to, outweigh the hydrogen side. What if I take this hydrogen and I take it out and I remove a bunch of hydrogen from the system? Then what? then my equilibrium, my container, my reaction is going to start to move this way. More ammonia will start to make more hydrogen and nitrogen gas because it wants to replace the hydrogen gas that's leaving. Okay, so consider this system where nitrogen gas and hydrogen gas are in a state of equilibrium to make ammonium gas. What's going to happen if I add more of this guy? If I add more of this guy, then it's going to want to shift to the right. It's going to want to create more product to kind of even out or potentially dilute the N2 that I'm adding. If I take this NH3 and I remove it out of the system, then again, it's going to shift to the right. It's going to shift to add more product because this time, for a different reason, it's shifting to the right. It needs to make more of this NH3 in order to keep this whole system here in equilibrium. Okay, so how does adding or removing gas affect the equilibrium position? Well, if we add in what's called an inert gas, and that's a gas that doesn't influence the reaction at all, then there's not going to be any change. We could add as much inert gas as we want. For example, helium, like helium in the balloons, if you take helium and you puff a birthday balloon down, it changes your voice, right? It makes your voice sound really funny, but eventually that just goes away. So there's no reaction going on with helium inside of your lungs. It's just the helium gas being present in your lungs allows the sound wave of you talking to travel at a different speed. And so then it comes out differently. Now it's what we call inert. Okay, it's just there's not reacting anything. But adding or removing gas, if it wasn't inert and it was part of the reaction, then it would basically affect it the same as concentration. So how does changing the pressure by changing the volume affect a reaction in an equilibrium position? All right, for that, it's time for another diagram here. Here I have two round bottom flasks. We also call them conical flasks. And there's another name for this one. This is called a comical flask. Because he's smiling. Anywho, inside of my two conical flasks, on the left-hand side I have NO2, nitrogen dioxide, and on the right side I have dinitrogen, do you know the other one? Tetraoxide, right? Okay, so this is going on inside of both of the containers. It's just that one container has more NO2 and the other container has more N2O4. All right. In this reaction, we have a color change. Actually, when more of this side is made, it turns brown in the presence of energy. And when more of this side over here is made, it turns more clear. Okay, so imagine inside of, we're just going to pick the container, this container. If I change the pressure, then basically I take the lid down and I kind of like squash everybody right there. Then I have now changed the space at which the molecules can move around. When I do that, when I decrease the volume, then it's going to shift towards the side that has the least amount of gas molecules or moles, which is the right side. See, there's 2 moles here, and this is just 1 mole, or there's 2 molecules for every 1 molecule of that. So if I decrease the volume and I increase the pressure, then this particular reaction is going to shift right. If I increase the volume, so I take this guy and I move him up here, and I increase the volume, and therefore I decrease the pressure, then this reaction is going to shift towards the side that has the most molecules. So in this scenario, it's going to shift that way. So if I, being that this one's a color change, if I increase the volume, I decrease the pressure, it shifts this way, it's going to turn brown. If I decrease the volume, which increases the pressure, then it's going to shift towards the side with the least amount of gas molecules, which is that one, and it will turn clear. All right, let's try this again with temperature. All right, most changes alter the concentration, but temperature does not change the concentration of a reaction. You basically are going to add energy to one side to increase the temperature. When you add energy to a reaction, it's going to shift towards the side that consumes energy. So let's just say I add energy to this side. If I add energy to this side, then I'm going to see a shift to what? To this side. If I add energy to N2O4, then my clear solution is now going to turn brown. If I don't add any energy to the entire system, then the chances are is that it will remain in equilibrium. So the irony is that this reaction that you're looking at right here is the reaction of smog. NO2, which is in our air, all right, remains in equilibrium with N2O4, dinitrogen tetraoxide. And when the sun comes up, right, and energy is added to the system, it moves to more NO2, nitrogen dioxide is made, and that's how we get brown smog. See, now I find that very cool. All right, catalyst. A catalyst is something that helps a reaction along, kind of speeds it up, right? But a catalyst in equilibrium will speed up the reaction, but it's going to speed the reaction up in both directions. So it's just going to approach equilibrium faster. That's what will happen. Okay, so let's do a Le Chatelier's example problem. Evaluate the following system and see what effects or stress that each stress will have on the system in equilibrium. All right, so A, is this endo or exo? Well, hopefully you saw that energy is going into the system right here. It's going endo. So this is an endothermic reaction. If I increase the temperature of this reaction, I take energy in and I increase the temperature, then it's going to shift to the right because it wants to get rid of all this extra energy. If I'm adding energy in over here, it wants to get rid of it. So it'll shift right. If I remove oxygen, if I take oxygen out of the picture, then it's going to move to the left. So it's going to shift left because it's going to want to replace the oxygen that's missing. All right. If I increase the volume, okay, so I'm going to increase V, I'm going to increase the volume, then that means that I'm actually going to decrease the pressure. And so that favors the side that has the most molecule of gases. So I have, or most moles. There's 2 here. There's 2 moles over here. I get that from the coefficient. And then there's 1, so there's 2 here. So this has no effect on anything if I increase the volume because they're equal amount of gas moles on both sides of the arrows. Okay, so if I add N2, so I'm going to take this guy and I'm going to add and I'm going to add and I'm going to add a bunch of stuff to the left-hand side. I'm going to add N2, then it's going to have too much stuff over on this side of the reaction, so it's going to shift right. It's going to want to make more product to outweigh all of its new extra N2 that's inside of its system. And so this is how we demonstrate Le Chatelier's principle on a system that is in equilibrium when we stress it temporarily with different things.